The CRJ 700 systems PowerPoint, that's most of what we cover in systems. So we are getting pretty close to catching up to our course outline. But we'll jump ahead here and we'll have plenty of time to get you guys up and running, ready for the practical and ready for flight planning, get a lot of flight planning in. So, but due to the tight schedule we're on today, I'm going to get started. Anything that's missed, we'll just have to make up in the recording. So I think we were on slide number 36. Yeah, flight controls. Okay. So the flight controls, we kind of went over this week one.
Are you going to put those slides up for us to see? I can't see them.
Oh, yeah. We just barely pulled up the PowerPoint, but so the flight controls, this is where we left off last night, was slide 36 here. So starting with flight controls, we talked about this in week one. We went over the primary flight controls. Please write these down. It is on the test. So write down the primary flight controls are elevators, rudder, ailerons, and multifunction spoilerons. So please make sure that you have those for the test. The wing is an advanced technology airfoil manufactured as a single unit and bolted onto the fuselage at 10 separate locations. So the kind of one of the things that you see on the 700 is the wing location is fairly far aft of the nose of the aircraft compared to a lot of other aircraft. You see the wings tend to be a little closer to the front. But anyways, kind of interesting how that is. So the secondary flight controls, we learned the primary flight controls are the rudder, elevator, ailerons, and multifunction spoilerons. The secondary flight controls would be, and these are on the test as well, so please take notes of what these are, but horizontal stabilizer trim, slats and flaps, and multifunction spoilers, not spoilerons, but spoilers, ground spoilers, aileron and rudder trim systems. So basically the trim, and then horizontal stabilizers, slats, flaps, multifunction spoilers, and ground spoilers. So yeah, make sure you have those written down.
Sorry, I'm late.
Oh, no, you're fine.
And I heard you say make sure you have those written down. What was that?
The secondary flight controls here.
Okay.
Just take a quick screenshot of those.
I did.
Okay, and then take a quick screenshot of these primary flight controls. Both the primary, we're going to ask on the test, we're going to ask what are the primary flight controls, and then what are the secondary flight controls. So,
thank you.
Yep, and Rex, this is the first slide that we were on. I saw that you were restarting your computer or whatever. Yeah, so we've only gone 2 slides, but
I'm going to sign in on my other computer, so I just got my internet back.
Oh, okay. So some of the key points. In an extreme emergency, the primary flight controls remain hydraulically powered by the AC motor pump 3B. Hydraulic, the 3B pump is the most important pump to remember. And we're gonna hit hydraulics, but the 3B pump is our emergency backup pump. Okay, so when all systems fail, the ADG, or air-driven generator that provides the emergency electrical power to the primary flight controls, that powers the 3B pump. Okay. The PCUs, or power control units, hydraulically move the control surfaces from mechanical inputs of the cockpit controls. So this aircraft is not a fly-by-wire aircraft. Some of you have heard of fly-by-wire. Basically, what a fly-by-wire aircraft is an aircraft that has actually no mechanical linkage between the flight controls in the cockpit and the control surfaces. It's all done using a computer system. So this is still the old-fashioned, hydraulically powered surfaces. So the multifunction spoilerons, and remember those are one of our primary flight controls, operate on the downgoing wing only to assist the ailerons in roll control at lower speeds. So the only time that those multifunction spoilerons are used are when we're actually at lower speeds. And it just assists, stability. The rudder travel limiter, or RTL, is installed to prevent the pilot from overstressing the vertical stabilizer. And remember, on the vertical stabilizer, what's the control surface on the vertical stabilizer? It's one of our primary flight controls. Remember, this is our vertical stabilizer. What's the control surface that we have on the back side of it here?
Rudder.
Yeah, the rudder. Exactly. So what the RTL is doing, the rudder travel limiter, nope, not slide 33. All that RTL is doing is basically making it so the pilot can't go full deflection on the rudder and overstress the aircraft. It stops it from completely going to the full deflection. Kind of funny, I had a pilot. He was a first officer. He was flying us back up from St. George, and he was adjusting himself in his seat and stepped on the rudder pedal and oscillated the aircraft really bad. So the aircraft slammed to the side. It's almost like a skid in a car, and it was just for a brief second, but I'm sure the flight attendant wasn't too happy in the back. I'm sure she got thrown around. But yeah. The flap system consists of one pair of inboard and outboard flaps. The flap positions, and these are important to remember. There's 5 flap positions: 0, 8, 20, 30, and 45. So 8 and 20 are used for takeoff, and 45 is used for landing. As you noticed, 30 is not in there. 30 is just an intermittent place. It's just basically to make it so that we don't go from flaps 20 to flaps 45 in one fell swoop, you know. When we talk about flaps 0, 8, 20, 30, and 45, we're talking about the angle of deflection. So this is 8 degrees, 20 degrees, 30 degrees, and 45 degrees. So, I mean, you all took geometry, I'm sure, but so it's just, you know, the 8 degrees is something like that. 20 would be it's a little bit more, 30 and 45, right? So that's all that it means by that. The leading edge slats, remember the leading edge slats drop off the front of the wing. And it consists of 3 panels on each wing. The inboard slat is the largest, outboard is the smallest. When required, the wing slats are anti-ice with engine bleed air. So just as a reminder, I know we had talked about this before, but the bleed air is just basically exhaust off the engine. They take a certain point in the engine and they actually will take the exhaust off the engine there and run it to different systems. Anti-ice, when we talk about anti-ice, we're talking about the leading edges of the wings and the engine cowls here. These are anti-iced. You can see those chrome surfaces. Those are all of our anti-iced surfaces. And what it does is that engine exhaust is extremely hot, like, 500 plus degrees. And they just pipe that exhaust along that surface of the wing. And the engine cowls there and heat it up. Because what happens is icing, and we'll talk about this when we talk about meteorology, but icing, when it builds on the wings of the aircraft, it dramatically affects the aerodynamics of the wings and can actually make it so a wing can't even generate any lift. It'll just fly like a brick, which isn't good. Hold on 1 second. All right, sorry about that. So, yeah. Yeah, anti-ice with engine bleed air. The slat positions, they only have two settings. The first one is 20 degrees, and the second one being 25 degrees, depending on the flap settings. So they work in conjunction with the flaps. So the way it works is the slats extend before the flaps, then retract after the flaps. So as you start lowering the flaps, the slats will automatically extend. The slats and flaps are electrically operated. The inboard spoilers work with the multifunction spoilers in operation of ground lift dumping systems. So what the ground lift dumping system is basically once the wheels touch the ground, the spoilers, they deploy. And if you look out at the wing of the aircraft, when you touch down, you'll see these panels lift up on the wing, and basically it makes like a wall on the wing. They just lift straight up, and what it's doing is it's dumping all the lift. So the aircraft doesn't want to keep flying, it wants to stay on the ground. And it helps slow the aircraft down. So the flight instruments, EFIS. Electronic flight instruments consist of 4 electronic flight displays. Each pilot has a primary flight display and a multifunction display. The primary display displays their airspeed and Mach, the vertical speed, altitude, attitude, heading, flight director command bars, navigation information, and autopilot information. So let me show you what that looks like. Yeah. So this is the CRJ's this is what it looks like. This is the information that's displayed. So when it talks about the attitude and altitude, or attitude, yeah, so the attitude is this right here. In the planes that like me and Rex flew, we called this an artificial horizon. What it's doing is it's displaying the aircraft's position and wing level relative to the horizon there. That red bar is the horizon. You can see 10 degrees. This one right here is 5 degrees, and then 2.5 degrees. So that's awesome. Mine does too. She gets red and starts cussing. This right here, this bar right here, this is our altitude. Okay. And this is our airspeed. So what you can see, this double bar here, this double pink bar, that is right here. That is the altitude at which the autopilot is set at. Okay. You can also see that up here. This is your autopilot information. Okay. The autopilot is also set for this. And then you can see here set for 0.77 Mach. And you can see that this bug right here, we call these bugs, are set for that 0.77 Mach. And you can see it rather than it displaying the Mach, it's displaying it in indicated airspeed. So you can see that 0.77 Mach at 40,000 feet is going to be about 230 miles an hour, or 230 knots. Remember how I said the higher you get, the slower your indicated airspeed will get, and yet your ground speed will increase. So This is the minimum decision altitude. So right now, the approach that he's going to be using, the MDA is set for 1,100 feet. So when he hits 1,100 feet, that's when, if you guys remember on the videos I showed you guys of people landing, whether it be a Cat 2 approach or whatever, you could hear it, the computer system call out minimums. That's what it's calling out, is the minimum decision altitude. Okay. This right here is our barometric pressure. We'll talk about that in meteorology, but basically anything above 18,000 feet, you go to what we call standard pressure. And sea level, at sea level, the standard pressure would be 29.92. That's what we put in whenever we're above 18,000 feet, so everybody's on the same altitudes. So reading the correct altitudes. So what this does is the higher this number goes, the lower this altitude will display. The lower this goes, the higher the altitude displays. So depending on what this is set at, you could be reading a different altitude. And when we travel from airport to airport, that actually changes. So when he drops below 18,000 feet, he'll start putting in the actual barometric pressure outside. Okay. This right here, this is our heading indicator, or HSI. And what it's doing is this bug right here, once again, the bug. This is the course in which the pilot has told the computer to fly. Okay, 248, you can see that that's at 248, and that's the heading that they're flying. Okay, it's getting that course from the FMS. So the pilot put in the flight plan. The flight management system is saying that 248. Okay, and it's saying that it's going to go 76.2 nautical miles on that course. Okay, this is what we call a vertical speed indicator. So depending on how quickly and how slow, like how quickly or slowly the pilot wants to climb or descend, this will show him the rate of climb or the rate of descent. So this is 500 feet per minute, 1,000 feet per minute, 2,000 feet, 4,000 feet, and the opposite going down here. Okay. Just so you know, 4,000 feet per minute, you feel like you're like looking straight at the ground. It's a pretty quick descent. Yeah, I mean, that's pretty much it. But the pink information that you see on this display will always be the autopilot settings. So that's what the autopilot's going to be flying, basically. Oh, and this red bar here, you can see this red bolded line. When the pilot exceeds this speed, it's what we call overspeeding the aircraft. The aircraft, depending on the altitude, can only go so fast, or depending on the configuration of his flight controls, like flaps and slats and stuff like that. This right here will move according to the configuration of the aircraft and the altitude. So if he goes into this red line here, he's doing what we call an overspeed, and he's overstressing the aircraft. The aircraft's not meant to go that fast, so bad things happen when they overstress the aircraft. Okay. The multifunction display, let me pull up what that looks like. So, Well, this shows all three. Yeah, but that's stupid flight simulator crap. I want the real life stuff. So the MFD is what we call it. Here, you can see it here. Oh, this one's good. Well, good enough. It's close enough to what it actually looks like. Okay, so the multifunction display, they can actually switch through. Actually, no. The multifunction display, this is showing them the course that they've planned. So this is the flight plan. This is the information that the pilots put into the FMS system. This shows the flight plan that the route of flight that he's selected, okay? So this is the Tris intersection, Shiro. This is TXK VOR. This is just showing him all of that information, okay? Oh, this is an FMS. No, that's displayed on the multifunction display. These little marks here, these are airports. If you see blue diamonds on here, you'll see these blue diamonds pop up with numbers next to them. Those are other aircraft. That would be the TCAS telling the pilot what's going on. So it will display the other aircraft depending on their altitude and heading. But that's pretty much what it looks like. So this is the course that they're planning on, or that they're flying. This is the heading that they're flying. This tells them their ground speed and their true airspeed. So their ground speed is going to be different than their true airspeed because the ground speed is taking in account winds. So true airspeed is just basically the airspeed at which we're flying. It takes like the altitude and stuff like that into account. The ground speed is actually how fast we really are moving across the ground. So depending on our winds, it changes. This information here is just telling the pilot that the next intersection that he's going to cross and the heading that he's going to change to will be 74 degrees, 25 nautical. Oh, no, I'm sorry, not that he's changing to. That's his current heading. And in 25 nautical miles, he'll be over the Shiro intersection. Okay. Kind of interesting how it all works, right? Okay. Just setting up for probably the next slide, I'm guessing. So the two data computers show pressure, altitude, static air temperature, total air temperature, ISA deviation, vertical speed, indicated speed, Mach number, true airspeed, and other system parameters. So that's what the computer systems are calculating. So each one of these we'll actually talk about. Most of them are to do with weather. Indicated airspeed we've already covered. Mach number we've already covered. True airspeed we've already covered. But this is all weather related information. And this changes these numbers down here. So these ones here change what's going on down here. Sorry, looks like 2-year-old drew it. So all works together to compile an accurate number for the pilot. The AHARS, gyro reference system that generates angular rate and linear acceleration. So this is what is the actual system that generates that artificial horizon that we use. It uses accelerometers just like you have in your phone. A lot more advanced, but still. So the gyro, depending on movement, will change. And I wish that we were in a classroom right now because I could show you guys using an old, gyro that we actually, you could actually feel the precession, but we have what's called gyroscopic precession. So whenever there's a change in direction on a gyro, it's felt 90 degrees opposite of where the change is made. And it's really hard to demonstrate that with a computer system. You can look it up on YouTube, though. Look up gyroscopic precession. I'll type it in here.
I'm going to probably need to see that in action because that didn't make any sense to me.
So that's what, in the chat there, gyroscopic precession. That's what it uses to determine our attitude and our bank angle and everything like that to produce the artificial horizon I showed you guys on the primary flight display. And similarly, that's kind of how your phones work as well, is an accelerometer. And it's like a gyro, but a little more electronically done than a it's done with a circuit, like an actual component, circuit card component, rather than an actual gyro. So combined with the heading from the flux detector, we can go back to the future. Our flux capacitor. No, the heading data from the flux detector provides highly accurate 3-axis AHARS info. So basically, with a gyro, the computer system can sense and recreate a 3-dimensional world with the computer. Because with flight, we're not operating in a 2D environment like we are in a car. Cars are very 2-dimensional. Driving's very 2-dimensional, unless you're rolling your car down a hill. That's the only time that it's 3-dimensional, but most people experience only 2 dimensions while driving their car. In an aircraft, we live in a 3-dimensional environment, so everything's done with roll, roll, pitch, and yaw. So AHARS consists of 2 computers, once again, 2 flux detector units, and 2 compensator units. And no, it's not compensating for anything. I know you were thinking it. Standby flight instruments. The self-contained integrated standby indicator, or ISI, provides backup attitude, altitude, airspeed, and magnetic compass information. So this is the backup to the AHARS. Okay. Also displays the localizer and glide slope data. You know what? It didn't talk about this. So this is what we call the ICAS. What the ICAS is these are engine settings. The N1 speed. Oh my gosh, I'm digging myself a hole. I can go off on a tangent here. Yeah, I think I'm going to go down the rabbit hole. second. So have you guys ever, do you guys know how a four cycle engine works? Like in your car or in a motorcycle? Anybody?
I will say yes.
So do you know what the 4 stages are?
Intake, compression, combustion, and exhaust.
Yeah, exactly. So it's the same in a jet engine. And we call it suck, squeeze, bang, blow. Is how pilots remember it. But so intake, we're just sucking in all the air. And then when we squeeze it, compression here. So intake is sucking all the air in. Compression is squeezing it. The combustion is our bang phase. Exhaust is our blow phase. So whenever we take air and we squeeze it and compress it, it gets extremely hot. It starts building temperature. You know, kind of like how a diamond's formed, you know, just that huge amount of compression. That's how we get the really hot air. Well, once it compresses and gets into a very small space and we ignite it, we add fuel in the combustion phase with that compressed air. It creates an explosion, a controlled explosion. So these chambers are actually just, it's a constant explosion basically. And then the exhaust phase is that's our thrust. Okay. So with a jet engine, we have basically 3 separate categories here, and I'll show you here that we're looking at. I mean, we're looking at a bunch of things, but the N1 speed, internal turbine temperature, and the N2 speed. Okay. So let's go back to our engine here. Our N1 speed is the fan blades in this compression stage. This is our N1, okay? N2 is the exhaust phase, okay? You can see here, this is like a drive shaft in your car, okay? Or a transmission. But what can happen is we can have these fan blades spin too fast, and then what happens is they spin so fast that we have what's called a compressor stall. And basically what happens is the fan blades are spinning so fast that it's not taking in air anymore. It stops this suction part, and we start having serious problems on the back end of the engine. When we have these compressor stalls, basically what happens is we lose all thrust. There's no more thrust, and it will shut down the engine. N2, it's similar in almost the same thing, but a little different phase here. But basically, if the N1 stage or the N2 stage starts spinning too fast, we stop producing thrust, and bad things happen inside the engine. It damages the engine. And so that's why on this screen, this is like almost always up. In flight, this will always be up. But what this is telling them is the speed of the N1 phase, the internal temperature, and the N2 phase. So the internal turbine temperature is just that the explosion phase. They don't want to get it too hot because then we can, just like in your engine, when it's running too hot, you start having, pings and stuff like that. It's kind of similar with a jet engine. Basically, we start having some really bad pre-detonation or things like that happen and can shut down the jet engine. So this is our warning system. So what happens is as systems fail on the aircraft, it starts building a list. It's color coded as well to show the importance of the failure. Things that are more important are going to be this dark red. Then we have an amber, then yellow. But these messages are just telling the pilot what's going on. This also shows the gear, whether they're up or down, or if we have a gear malfunction, what gear malfunctioned, what landing gear malfunctioned, whether it's the two main wheels or the nose wheel. This is our flap setting right here. I'll clean these up real quick for you. Okay, so you can see right here, he's currently flap 0. This tells him the total fuel on board. He's got 2,000 pounds in the left wing, 2,000 pounds in the right wing, and 20,050 in the center tank. So he has a total combined fuel of 24,055 pounds, which is way more than a 700 can hold.
The math isn't working there. It says 2,000, 20,050, and 2,000. It says 24,055.
Yeah, there's always some residual in the tanks, and that's probably just counting for the residual.
It's about a half a gallon.
Yeah, but there's a tolerance that they're allowed as well between the displays. So here you can see the oil pressure and oil temp, also very important stuff. And this is their fuel burn per hour per engine. So this engine's burning at 1,585 pounds per hour, and this one's burning at 1,585 pounds per hour. Okay, this is what we call a synoptic page. This is showing, a couple different things. This is showing the fuel system. So it's telling us the temperature of the tanks, how much fuel we have in each one of the tanks, and then the temperature of the lines going out to the engines. This will also show whether or not the APU is running. But anyways, yeah, fuel used and total fuel on board. I don't think so. That's not a CRJ. Anyways, doesn't matter. So these synoptic pages, there's also one that will display the hydraulic systems, the pneumatic systems, the doors, whether they're open or closed, the environmental control system. They can flip between these pages and see what's going on. So if they have a failure over here, they can, and it's one of these systems, they can flip to one of those pages and see where the failure is happening. So anyways, fun stuff, huh? So let's talk about fuel real quick. Fuel tank, there's 3 tanks. As I said in that last screen, 3 tanks. You got a left, right, and center tank. The 2 tanks on the left and right are in the wings. And the center tank, of course, is in the center in the fuselage down by where the cargo bays are. The fuel supplied to the engine flows through collector tanks. So there's like a center holding tank that will flow the fuel to the engines to help manage the fuel flow between the tanks. Fuel is heated by high temperature engine oil passing through the heat exchanger. So that's how when they're flying at 40,000 feet and it's negative 63 degrees up there, that's how they keep the fuel warm enough to stay as a liquid. It's just by basically flowing oil over the tubes that the fuel flows in. Fuel distribution. The engines and APU have separate fuel distribution systems, just as I showed on that ICAST screen. Engine fuel flows from the collector tanks utilizing the motive flow and main ejectors. DC boost pumps are used to move the fuel during engine start. So they actually use like their battery, the DC power to boost for the fuel pumps to boost the fuel over to the engines. Once the engines are started, then it basically will. I think it converts to an AC pump, but the APU fuel flows from the left collector tank utilizing DC electric fuel pump. So cross flow is accomplished by using powered and gravity systems and is used to balance the wing tank quantities. Maximum fuel imbalance for takeoff is 300 pounds and 800 pounds for all other times. So when they're taking off, they can only have a 300-pound difference between the right and left tanks. The center tank doesn't matter as much because it's in the center, right? The center of gravity, or it's staying centered. But if we have a 300-pound imbalance between the wings, then one wing's going to want to dip more than the other. Fuel is transferred automatically from the center to wing tanks. Then the wing tank fuel level drops to 94% of capacity. Fuel system computer initiates transfer automatically. So they want to keep that balance. Okay, so since we're at hydraulics, I don't know if everybody heard me at the beginning of the meeting. We're going to watch part 2 of that series that I had you guys start on. And then after that, you guys will take your 20-minute lunch or dinner, and Adam will be on. Actually, you guys can probably just eat your dinner while you're sitting at your computer, but keep your go-to meeting up, and Adam will be on at 7:30 to finish off the class. So he'll take it from hydraulics down to the rest of the class, through the rest of the class. But I've got to head out, and yeah. So let me post that video. Let me see. You guys, just forgot the name of the series. Oh, City in the Sky. Okay, so there's the video link. Like I said, Adam will be on to take over class, and he'll be on at 7:30. He'll just pick up right at that hydraulics and carry you guys through the rest of class. But watch that video, enjoy, eat your dinner while you're watching it, just to keep things flowing for the rest of class. But I will see you guys tomorrow, and tomorrow we will finish off systems, most likely. So any questions? All right.